I'm going to be talking about three projects this afternoon for the next 25 minutes or so. And the topic of scale in the context of these projects is very important. I wear three integrated hats. One as an educator, one as a researcher, and also as a designer engaged in built experimental practice. I frequently find myself in spaces that are not typically frequented by architects. This is an image that was taken during the first day of a course that I taught for 4 years within the Graduate Department of Architecture at Penn Design in Philadelphia with a cell and molecular biologist, where we paired graduate architecture students with postdocs and PhD students in the context of the lab setting. And I'll be talking about that more specifically in just a moment. Now, this is the paradigm that I operate within. My own expertise is within what's called design computation, which if you begin to delve a bit deeper into that, these three primary terms define what computation is. And I'd just like to pause for a moment to explain what those terms are if you're not familiar. I'm very interested in generative processes, specifically looking to nature for design models to apply those models in the context of architecture. So generative being bottom-up, rule-based, and based on relationships. So I frequently may not necessarily know what the final form will be, and the starting point, obviously, is frequently very simple. Now, within a design process, I may begin to tame those generative processes with parametric strategies, which are hierarchical. They're associative, so what happens upstream affects downstream and vice versa. And then that may be further focused through optimization tools, such as looking at a solar sun path diagram to optimize, say, for example, a facade design against the path of the sun. And then the fourth term, matrix architecture, is something that we put on the table, which is the visualization and simulation of complex dynamic form and function in context. Now, I also operate within the paradigm of making. I have a background in ceramics. I have a BFA in ceramics and a BA in painting. And I'm very interested in how issues of technology and information and data are melded with the constraints that come into the fold through issues of making, craft, fabrication, and so on. And within that context, I've been working within weaving for about 8 years, looking at datascapes and body architectures. My interest in weaving is twofold. The first has to do with a long lineage of relationships between architecture and weaving, from the work of Gottfried Semper to the early modernist period, specifically looking at what was happening in the weaving workshops at during the Dessau years at the Bauhaus. And then secondly, my interest is looking at a longer history between computation and weaving in terms of its pattern, geometry, and fabrication. And some of you may be familiar with a very interesting story which looks at the mechanization of the Jacquard loom. Now, Joseph Jacquard, who is the son of a weaving family, was determined to mechanize the loom because he actually hated spending time in the weaving mills. And so he was determined to mechanize the process. And he invented the punch card, which effectively controlled the flow of information through the over and under of warp and weft, and ultimately specific patterns and geometric expressions. Now, he had a common friend, Ada Lovelace, who was familiar with Charles Babbage, who at the time was inventing the first steam-driven computational device. Now, Ada thought, well, what if we brought these punch cards to the first steam-driven computational device? And to this day, she's credited with being one of the first computer programmers. Now, these concepts actually influence the very first mainframe computers. In fact, IBM named one of their primary and first computer programs Ada. So taking these two interests, I delved into a body of research looking at how those concepts could be married with contemporary digital techniques, designing my own scripts. I like to think of software as a new material in and of itself, thinking about how pattern and geometry and code is melded with the three-dimensional and spatial expression, working with various mathematical series such as the Fourier series, and weaving with sine and cosine waves, taking advantage of their orthogonal mathematical nature that through iteration achieves much more complex and beautiful and intricate results. And this essentially informed a pattern book, which I applied to a series of projects, and I'll just talk about one very briefly. In 2006, which was at Artist Space here in New York City, and the project was called Foyer Tapestry. Now, within all of that research, I was very interested in probing data and thinking about the intangible inherent spatial qualities of data and how they might be revealed in a new context, specifically looking at weaving. And so I worked with various mathematical series, but specifically looking at the linkages between music, harmonic systems, and how that could be captured and woven in real time, thinking about what is generative fabrication. And so these were some of the early diagrams that informed the Foyer Tapestry. And then finally, what was produced were a series of draft notations which control the over and under of warp and weft, which were met with the CAD-CAM interface of a digitized Jacquard loom. This is an image taken of a digitized Jacquard at Philadelphia University. It's one of the oldest textile engineering and design schools in the country, and I've been fortunate to collaborate with them on several projects. And interestingly enough, the interface works quite well with various CAD-CAM processes that we work with in the context of architectural form production. These are a few images of the final piece. It was displayed in conjunction with Hedge, which I was a co-designer on, which is a three-dimensional tensegrity structure, which also can be considered as a woven construct in terms of looking at the flow of forces, tension forces moving throughout the components. The overall tapestry was 36 feet in length and about 6 feet in width, and featured 8 iterations of the same algorithmic process, so looking at 8 different outputs of that original Fourier series, inspired by harmonic systems, and just a few details. Now, this interest in looking at the intangible notions of data informed the early beginnings of research collaboration that I started with Dr. Peter Lloyd-Jones, who's a cellular molecular biologist. I'm now based at Cornell University as a professor, but I taught at Penn Design for 6 years, and during that time, I launched Lab Studio with Peter. And in the beginning, we didn't have a set agenda. We didn't necessarily know what the results were going to be in terms of the applied projects, both on the scientific and design end of things. But we were very interested in generating a philosophical space, a space for making, a space for thinking, so that we could bring back new ways of seeing in our own fields. Now, these were some of the terms and methodologies that began to emerge in the context of our discussions. We spent about a year actually just joining each other's reviews. I attended all of the lab meetings at Peter's lab. He attended my studio reviews in the graduate architecture department. And we realized that the common bridge that we had immediately available to us was the topic of visualization. Now, across disciplines, we are finding that we're all very good at producing data, but we're not very good at making sense of data. And so what we were able to bring to the table, myself and my graduate architecture students, was a way of seeing and thinking systemically through design problems that was different, but also was readily applicable to some of the visualization strategies that were necessary in the context of the lab. So we brought our modes of thinking and seeing, but also our expertise in terms of visualizing in 3D over time and in space through various parametric and 3D modeling programs. Now, over the course of that year, we then formalized Lab Studio. We brought on 3 graduate architecture students to work with us, and then that formed the foundation for the course that we taught for 4 years. I'm now collaborating with a number of scientists, material scientists, systems engineers, physicists, And in the last 8 years, our research strategy and design strategy has become formalized. And the topic of scale, as you can see in these three stages or phases, is incredibly important. So we start with the production of new tools and forms. That then moves into architectural prototyping, and then on the architectural side, we begin to probe how that might impact the production and form of buildings. So how do we start? We may start working with the data directly, coming from the cell biologists, coming from the material scientists, or we may extract a set of rules and relationships that inform an abstract modeling or simulation strategy, such as you can see here, which is inspired by a series of networking cells in their extracellular matrix environment. We also work with various fabrication strategies, 3D printing. I like to work with 3D printing not as a representational tool, but as a way of probing part-to-whole relationships. I'm thinking about, again, generative fabrication. How can we design and make and fabricate in real time? And I'll talk about one project that has come out of 3 primary research tracks to begin with, which stemmed from looking at the blood vessel development, or simulating dynamic biological systems via design. Now, some of the early data sets that we began with are not all that dissimilar to what you see here. This is the data set that inspired this project. And what you are looking at are networking endothelial cells that form the vascular lining of the human lung. I'm just going to go ahead and play that one more time. Now, the concept that we were very interested in, and at the beginning, and this continues to inform a number of my research projects, is the reciprocity between the cells and their extracellular matrix environment. You can actually see how they're signaling through and pulling up on that protein-rich matrigel environment. Now, this reciprocity of looking at how context specifies form, function, and structure in cells presents a series of powerful ecological models for architects such as myself and my students to probe. I'm very interested in looking at the human body as a place for discovery and the production of potent biodynamic models so that we may begin to think about issues of adaptation and performance in a new way in the context of architecture. So this project was developed in 2008. It was titled Branching Morphogenesis. I was invited to exhibit some of my weaving work in the design and computation galleries at SIGGRAPH. And I said, well, that's fine and good, but I want to do a new project. And so we launched into this project. We didn't have much of a budget. In fact, we didn't have a budget at all. But we started with a series of simulations. This was produced in processing, which many of you are probably familiar with. And I had a couple of questions. I was not interested in visualizing and modeling the cells or features themselves, but more so looking at the complex networking environment that they were moving throughout and signaling through, which you can see visualized through this deforming grid. And thinking about issues of morphology, how form changes over time and in space. I was also very interested in the topic of scale and slowing down the visualization process through analog modeling by bridging it with issues of making and fabricating and integrating both analog processes as well as digital processes. And so we settled on several templates, imagine them as slices through time of that networking environment. The densest areas of the field were rendered in red, as you can see here. I had always wanted to do a project with cable zip ties. They're ingenious components in their ability to adjust locally and inflect globally. We didn't have much of a budget, and I was also very interested in the capacity of the zip tie as a ready-made to reach diverse audiences. The fact that everyone knows what a cable zip tie as a device could actually engage people that may not necessarily be interested in topics at the intersection of science, design, and art. It was composed of over 75,000 cable zip ties. It was produced over the course of a month. I was there every single day with my students. And we worked with giant templates at a 1-to-1 scale. We produced a series of material study models before we even began to filter the data through the material system. And this was the system that we settled on, which was composed of 3 different sizes of cable ties, which formed a surface, and the joining factor was normal to that surface, as you can see with the smaller ties that are red. These are some of the final installation shots. The densest areas of the field were connected with tubular forms that were also formed with zip ties. Gallery visitors were invited to meander through and between each of the sheets. There were a total of 5 sheets. The overall installation was approximately 18 feet in height, 12 feet in width, and 10 feet in breadth. We were later invited to exhibit the piece at Arts Electronica in Linz, Austria, at their inaugural opening of their new building. Arts Electronica is a very interesting institution which has been around since the early 70s and has always been interested in looking at the nexus of science, design, and society. Now, at the same time, some of those same tools that we were producing for modes of visualization were being applied in the scientific context towards various problems on the other end. And that was something that was very important to us from the very beginning in terms of thinking about how we would produce applications both in biomedicine as well as in architecture and design. And we were fortunate to win first place in the NSF AAAS Visualization Challenge in 2009 and was featured on the cover of Science. Now, one of my most mature research projects, which has definitely been influenced by some of the topics that I've just discussed with you, is titled eSkin, or Multiscalar Design Ecologies. In 2010, the National Science Foundation launched a call for collaborative teams that would include architects, and it was the first time that they had ever done that. And the topic that was of concern is sustainability, and thinking about issues of performance in buildings. But they were interested in not just taking the topic of sustainability in terms of its technical ramifications, but in rethinking the whole conceptual project around the problem. And so the call was inherently to bring together transdisciplinary teams that could probe the problem with new ways of thinking and seeing. And so we took it as an opportunity, and we're fortunate to be awarded one of the $2 million grants. There are 10 teams across the states. It's a 4-year grant. We're in the 3rd year or 2nd year of the grant currently. The full title of the project is Energy Minimization via Multiscalar Architectures from Cell Contractility to Sensing Materials to Adaptive Building Skins. This is just a quick look at the full team. It includes cell biologists, material scientists, myself and my graduate and undergraduate architecture students, systems engineers, as well as other architects as consultants. Now, this dynamic reciprocity, which I mentioned previously, is really at the crux of our starting point. Our emphasis rests heavily upon the study of natural and artificial ecology and design, especially in observing how cells interacting with pre-designed geometric patterns, which are being produced in Dr. Xu Yang's lab, who is the material scientist, how those patterns are altered by this fine-scale design ecology elicited by human cells being plated on these substrates. And importantly, we're interested in the new surface effects that are produced within this context. The project overall harnesses tools and modes of design thinking and applies them towards the design and engineering of passively responsive materials, sensors, and imagers. This is pretty much where we're at right now. Specifically, we're interested in exploring issues of materiality from nano to macro scales based upon a quantitative understanding of nonlinear and dynamic cell behaviors on geometrical substrates. Now, we're not going to have human cells on buildings, but we're interested in looking at and observing the behaviors of cells on these substrates, how they manipulate pattern, how they manipulate geometry, what happens when we change the compliance and and making of these substrates, how does that impact, say, networking behavior of cells? And through the expertise of the systems engineers and electrical engineers, how might we begin to harness that and embed that into sensors and imagers at a macro building scale? Obviously, central to this proposal is the reduction of the overall carbon footprints in the built environment, while also addressing important social and community-based topics that arise through large-scale transformations of building facades against environmental constraints. Now, we're not only interested, obviously, in the functional capacity of these thin building skins, which is our end goal in terms of how they will negotiate heat, light, and moisture, but we're also interested in the topic of personalized architecture and the beautiful effects that these materials may exude. How might rooms adapt and change in real time within the presence of ourselves as individuals as well as a collective? Now, the insights from understanding how cells modify their underlying substrates will lead to the rational design and engineering of passive materials and integrated with smart sensors and optical and electrical circuits for new paradigms of responsive building skins. These are some of the parameters that we're working with. We're interested in how these skins within facade systems in buildings will respond to proximity, the proximity of us. And we posit that these skins can be integrated within new building construction as well as within existing building construction. Obviously, we're very interested in how these patterns and geometries respond to the sun, as well as to issues of touch, haptic qualities. And then just a couple of slides to highlight the expertise of the team. This is a slide for Dr. Xu Yang's lab and her expertise. She's engaged in biomimicry and very interested in looking at issues of structural color, probing insects such as the wings of butterflies, and observing how changes in pattern and geometry also alter color, and how those strategies can be harnessed and scaled up towards the design of materials in various applications. She also looks at the feet of gecko as well as lotus leaves to produce superhydrophilic or superhydrophobic materials, water repellent or water absorptive materials. Nader Ngata and Jan van der Spiegel, the electrical engineers on the team, also engage biomimicry. They're interested in looking at how insects see light. Many insects see polarized light. We don't see polarized light. And so they harness these topics and concepts and bring them into the world of sensing mechanisms, the design and engineering of those sensing mechanisms, as well as imagers. They've effectively made some materials turn invisible in the presence of our sight. So you can imagine the implications of that at the scale of architecture. What happened to my building? And I'll just conclude with the last couple of minutes with a very new project. It literally just opened a week and a half, 2 weeks ago, here in New York City. It's currently on view Thursday through Sunday at the Nike Stadium at 276 Bowery. I was invited by Nike, or commissioned by Nike, last spring to become a part of what they are calling the Nike Flynet Collective. And there were 6 artists and designers, innovators from around the world that they invited to essentially riff on a new technology that they've developed, which is knitting shoes. Now, the concepts or benefits, core benefits of that technology, which are performance, form-fitting, sustainability, and lightness, are certainly concepts that are of importance in architecture. And so when I was commissioned to become a part of this collective, I decided that for my project, and this was to be in New York City, it is in New York City, would be engaged in the simplicity of knitting, its geometry, its pattern, how it's fabricated, both in analog terms as well as digital terms, how that could be married with the complexity of the body in motion, and bridging what may be thought of as disparate fields, sport and architecture, in a meaningful way. And so we structured several workshops over the course of the summer The first workshop was all about collecting data. We had various activities where the participants engaged in, went out into the city. We outfitted them with various sensing devices to capture human motion data. That then informed a series of visualization strategies, and I'm not going to go into too much depth on this, but I thought I would show you some of the images that were taken at the night of the opening, which ultimately informed the final pavilion, which is composed of over 300 whole garment knit elements, which are seamed together to form a soft textile-based interior, which is brought into tension with the aid of an external frame system, which you can see. I have a better image. Well, here, which is composed of circle-packed rings. All of the tubes, which are based on individual human data, then become a part of a collective overall. The yarns feature 3 reactive materials: solar active, photoluminescent, and reflective, which is why you see this sort of change in terms of the material geometry and patterning as an overall environment. So this is the same shot, just at a different time where the photoluminescent threads are being activated. And I'll just conclude with this final slide, which brings me back sort of full circle to that 4th term, which is matrix architecture, which is embedding material systems with biological relationships and behaviors to generate models that are at once natural and artificial, and give rise to the production of built interfaces and hybrid ecosystems at multiple length scales. Importantly, it's also about breaking pedagogical boundaries through shared collaborations in design and science to generate context-driven tools, models, and modes of seeing within an ever-increasing information context, which certainly, I think, touches many of the shared concepts and interests that flourish within Maker Faire. So I'll conclude with that. I think I have a couple of minutes for questions if you guys have any. Thanks. Any questions? Yeah, no, it's a great question. I didn't talk about that in this short talk. As I mentioned, producing deliverables on both sides was very important from the very beginning and continues to be so. So on the scientific end, I would say that visualization and modeling is still very, it's at the forefront. And so we're engaged in producing diagnostic tools to look at, say, how motile behaviors of cells change over time. So, for example, your cells move differently from my cells. Could we use that as a way of diagnosing particular diseases in a less invasive way? And so we've helped with identifying cell dances, if you will, identifying choreographies and different types of behaviors. So that's one thing. And in fact, the student who started that, she was one of the first 3 graduate architecture interns in Lab Studio, Erica Sabin. She graduated with a master's in architecture. She's now working on her PhD in cancer biology at Stanford. So, that's really exciting for us. So that stuff is going on. In terms of the material scientists, modeling, obviously still very important. In the context of the eSkin project, we're developing a series of simulation tools that bridge environments such as Ecotect and DIVA to understand, solar heat gain in real time, so that data can then be embedded into their design material substrates. To be honest, I was blown away by what wasn't being done when I started collaborating with Peter and now many others. I mean, I just sort of thought that they would be much more sophisticated in their modeling and visualization than we are. But that wasn't the case. And so we teach each other. I mean, there's a whole field in biocomputing that certainly is very much invested in some of these ideas. But I think it's the way that we think through design problems, albeit now at a radically different scale, that is actually the most beneficial. So some of our tools we've attempted to patent as software packages on the scientific end. So there's a lot of sharing now going back and forth. And like Rhinoceros, which is probably familiar to many of you, is our sort of bread and butter program. It's now on the desktops of a number of the scientists. So there's a lot of sharing occurring and the kind of productive misuse of technology. Yeah. Thanks, everyone.